Hey folks, Professor Gray here with summarizing and graphing data, visual depictions of data. Well, why do we graph data? A couple of reasons. The visual depictions organize the data and make them easier to read. Both as a researcher and as someone who is reading research, if your data is graphed and organized in a visual depiction, then it's easier to read the data, the numbers that are associated, and it's also easier to read them if you are a researcher. If you're putting your data together to do something with it, it's just more easily accessible. Also, visual depictions of data can reveal things about the behavior of the data, in particular the distribution of the data, which will be important as we travel further into statistics. Well, here are some terms to get us started off. Frequency is how often something occurs. How frequently did you go to the store last week? Well, that's the number of times you went. So frequency is just how frequently something has happened. Variation tells you how much the data values vary from one another. If there's a high variation, then they vary from each other, or they're different from each other very much. If there's a low variation, then they kind of all are around the same values. The distribution of data is the nature or shape of the spread of data over the range of values. So some of these are bell-shaped, uniform, symmetric, or skewed. That's how the data looks, how it is spread out when you look at the entire range of values. Now, outliers are values that are very far away from the vast majority of the other values. They lie outside the rest of the values. They are the oddballs. They're the ones that are either extremely high or extremely low. Well, one type of visual depiction of data that we find incredibly useful is the frequency distribution. Now, some textbooks call this the frequency table. And it shows how a data set is partitioned among several classes. So in this particular example on the slide, on the left you have the different classes, 1 to 10, 11 to 20, and so on. And then it lists all of the classes along with the number of data values in each. So, for example, in this example, there are 3 numbers of units produced between 1 and 10. There are 34 between 11 and 20. There are 45 between 21 and 30, and so on. Now, frequency distribution does not maintain the original data values. I don't know what the 3 numbers are that are between 1 and 10. I just know there's 3 of them. So I don't get to see the original data. I don't see the whole list of numbers. I just see a summarized version of them in this table. So let's do an example. Here are the pulse rates in beats per minute of a number of females. Here is that same information in a frequency distribution. Now, which one do you think is easier to read? The entire list of all of these sample pulse rates, or the pulse rates as they are organized into a frequency distribution? As you can tell, the frequency distribution is much more accessible. We can easily look at the frequency distribution. We can tell, well, there's 12 numbers between 60 and 69. There's 1 pulse rate between 100 and 109, and so on. We can tell that just by looking at the frequency distribution, and that's part of the point. You want your reader to be able to look at a frequency distribution and immediately get things from the data. And if you're a researcher, you want to be able to organize your data in such a way that you can see trends and you can see the distribution and behavior of the data over the range. Frequency distribution makes that easier to do. On the right-hand side of the table, you have the frequency. Frequency for a particular class, the number of original values that fall into that class. Again, we don't see the original values, just the frequencies. Here's some other terms. The lower class limits are the smallest numbers that can actually belong to different classes. That would be 60, 70, 80, 90, 100, 110, 120. The ones on the left in the classes. And these classes are inclusive. So if a 60 is one of the numbers in your sample, then 60 would belong to the first class. We include those numbers. As expected, the upper class limits are the ones on the right. Those are the largest numbers that can actually belong to different classes. Class boundaries are used to help separate the classes if you are making a frequency distribution. Basically, we just go a half step between each class. That helps us realize, well, if I have a number like 69.4, well, that would round down to 69, so I would put that in the first class. If I have a number like 69.7, that rounds up to 70, so I would put it in the second class, and so on. Class midpoints, as the name implies, are the midpoints of each class. So the number between 60 and 69 is 64.5. The number between 70 and 79 is 74.5. Between 80 and 89, 84.5, and so on. Oh, by the way, how do you find a midpoint? If you have two numbers and you're looking for the number that falls in between them, then you would add the lower number to the upper number and then divide by 2. So 60 plus 69 would be 129. Divided by 2 is 64.5. Class width is the difference between two consecutive lower class limits or two consecutive upper class limits. For example, the difference between 70 and 60 is 10. The difference between 99 and 89 is also 10. The class width occurs when you subtract one of the upper limits from the one right below it, or one of the lower limits from the one right below it. And the class width is consistent for all classes, both the lower class limits and the upper class limits. Here are a few steps for making a frequency distribution, now that we know what one is and kind of how to read it. First thing you do is you sort the data and determine the number of classes, and it's usually between 5 and 20. Now, if you get an assignment from me, you're going to know how many classes to use. 9 times out of 10, those will be in the instructions. But we try to pick a healthy number so that we can actually get a good idea of how the distribution is spread out. Then we calculate the class width, and the formula for class width is at the bottom of this slide. You take the maximum, it's the largest number in your data set, subtract the minimum, that's the smallest number in your data set, then divide that difference by the number of classes. The brackets around the class width are ceiling brackets. They're there to remind you that if you get a whole number for class width, then use that number. But if your number is a decimal number, such as 5.00001, always round up to the next integer. Yeah, the reason for that is so that you don't run out of classes before you run out of data to put in them. So always round those up if they are not a whole number. If they're not whole numbers. Step 3, choose the minimum data value as the first lower class limit. Lower class limits are the ones on the left. The first one will be on the top left. Then using the class width, add and list all the lower class limits, so all the ones on the left. Then list the upper class limits. We'll fill those in using a little bit of logic and the class width. And lastly, once your table is pretty much made, enter the frequency of each class to finish it up. These steps actually go pretty quickly, so let's do an example. Example number 1. The data below describe the weight in pounds of wild bears between the ages of 8 months and 177 months. So we've got bear weights. Make a frequency distribution consisting of 6 classes. So at the bottom right, I have all my data. And for this problem, the data is already in order. And hey, that's great whenever it is. If that data were not already in order, I would need to sort the data. That's step one. Sort the data to determine the number of classes. I would need to put those in order. That's going to make my life much easier when I make this table. You can either do that on your own just by looking at the list of information and listing them back out in order. You can use a program like Excel or StatCrunch or Minitab. However you want to do that. Using software is certainly faster, especially if you have a large data set. But either way, once those are sorted, we're good. And we know how many classes to include because it's in the problem. We'd like 6 classes. Alright, step 2 is calculate the class width. That's the maximum minus the minimum divided by the number of classes. So here we go. I first off need the maximum, my largest bare weight, that's 442. So class width equals, 442 minus the minimum, which was 26, and I'll divide that by the number of classes, which was 6. If I get a whole number, I'll leave that alone. If I do not, I'll round it up. So 442 minus 26 divided by 6, because that's my number of classes. If I pull out a calculator or do that on my own, I get 442 minus 26 is 416. Divided by 6. And that gives me 69.3 repeating. Well, I don't want a class width that's a decimal, so we'll round that up to 70. 70 is my class width. So when I go over to my frequency distribution table, on the left I'll have my weights. On the right I'll have the frequency. And it's always good to add a title. Weights of bears, for example. And my class width will be 70. Next step. I'll choose the minimum data value as the first lower class limit. My minimum data value was 26. So 26 is my first lower class limit. Now to find the next lower class limit, I'll add 70 to 26. That makes 96. Then I'll add 70 again. That's 166. Add 70 again. I get 236. Add 70 again. I get 306. And if I add 70 one more time, 376. Those are all just the lower class limits. I got to fill in the upper ones now. As a matter of fact, that's the next step. Using the class width, list all the lower class limits. We've done that. Now list the upper class limits for number 5. So for the upper class limits, well, if the second class starts at 96, my first class would have to end at 95. And if my third class starts at 166, my second class has to end at 165. And I could just follow this pattern. Keep going using the same logic. Until at least I get to the bottom. Now I don't have another class to look at for the very last upper class limit. So what am I going to do? Well, remember that your class width, that would be the 70 we found earlier, has to stay consistent throughout all the upper and lower class limits. So the last upper class limit will be 70 more than the next to last upper class limit. So that makes it 445. Last thing to do is to fill in the frequencies. And for this part, well, we just take a look back at our data and see how many data numbers are between each class. So 26 to 95, there's 1, 2, 3, 4, 5 of those. 5 numbers fall within that range, so that's my frequency. 96 through 165. 1, 2, 3, 4, 5, 6 of those. There are 6 numbers that fall within that next class. 166 through 235. Oh, look at this. 166 is repeated. That's okay. You count it both times. So 1, 2, 3. How far am I going up again? 1, 2, 3, 4, 5, 6, 7 is my frequency for that class. 136 through 305 is next. Or excuse me, 236 through 305. There's exactly one of those. Next class, 306 through 375. There's 1, 2, 3, 4 of those. And last but not least, 1, 2 are left. That will go in the last of the classes. All right, well, how many different data values did I have? I had 1, 2, 3, 4, 5 times 5 is 25. What do you think I'd get if I added up all the frequencies in my frequency distribution? Yeah, I should get 25. And 7 plus 1 is 8, plus 2 is 10, plus 6 and 4 is 20, plus 5 is 25. That's a good way to check and make sure that you've got all the numbers accounted for. Every number that's in my original data set is now accounted for in my frequency distribution. It is completed. That's how you make a frequency distribution. Now, in some cases, you may see frequency distributions that have more than just 2 columns. Maybe you have your classes, your frequencies, cumulative frequencies, relative frequencies, and so on. Well, the process is the same to start it off. For those other columns, we would just make the necessary calculations to fill those in. Here's a cumulative frequency distribution. It's mostly the same as a frequency distribution. One of those is on the left. The cumulative frequency distribution is on the right. But the difference is that I have cumulative totals as I go. So 12 is the first frequency, then 12 plus 14 is 26, and so on until I get to the very end. In a relative frequency distribution, instead of numbered frequencies, instead of counts, I have relative frequencies or percentages. In this particular example, the one on the left is the frequency distribution, the one on the right is the relative frequency distribution. In the first class, I've got 12 as my frequency, so 12 out of 40 total is 30%. In the second class, 14 out of 40 total is 35%, and so on. 0 out of 40 is 0%. I get that by dividing the frequency by the total and converting that to a percentage. Well, frequency distributions are very special because they can be used for both quantitative and categorical data. Now, some textbooks call that qualitative data. The frequency distributions can be used for both types of data. Here on the left, hey, there's a familiar frequency distribution. It's the weight of the wild bears that we just did. A little less messy, though. That one's been done in Excel. And on the right, I've got first graders' favorite colors. The weights of wild bears are quantitative. You can count them or you can measure them. They even have a unit of measure, pounds. The ones on the right, colors, are not quantitative. Those are categorical. They're names, labels, categories. I can use frequency distributions to organize both types of data. And I can tell some things immediately by looking at these frequency distributions. I can tell the most frequent class in the weights of wild bears, that would be the 166 to 235 range. I can tell that the least number of bears were between 236 and 305. For the colors, I can tell that the most popular color, or the modal color, is blue. The least popular was purple. A dot plot is another type of visual representation that can be used for both quantitative and categorical data. In a dot plot, you literally dot plots or plot dots. That's a graph in which each data value is plotted as a point or a dot along a scale. And dots representing equal values are stacked up. Here's the pulse rate of the females again, same example or same data set. And I've stacked up dots for 60. There were 3 females that had a pulse rate of 60. There was one that had a pulse rate of 96, one that had a pulse rate of 104. There were 1, 2, 3, 4, 5, 6 that had a pulse rate of 76, and so on. Now, the beauty of a dot plot and some other types of plots we're going to learn about is that the original data values are maintained. I can see the original values in the data set. I don't get that with the frequency distribution. And I can get a pretty good idea of how this distribution shapes out. It looks like it starts low, goes high, comes back down, and then it really trails off towards the upper end. As a matter of fact, this 124 here on the far right just might be an outlier. The 104 might be as well, for that matter. A little bit later on, we'll learn how you can tell if they are truly outliers. Dot plots are special because they can be used for both quantitative and categorical data. Pulse rates of females, that's quantitative. You can measure or count it. Below that, I have another dot plot. This is a number of snakes in a zoo. The names of the snakes are names. They're categorical. But I can put them in a dot plot. For example, there's 4 black cobras in this zoo. There's 2 anacondas, and so on. And I can tell that there are more rattlesnakes than anything else. That would be the modal class. And there are fewer anacondas than any other type of snake. So frequency distributions and dot plots can be used for both quantitative and categorical data. That's not true for other types of graphs and charts. There are other types of graphs and charts that must be used either for quantitative data or categorical data, but they cannot be used for both. So it's important to be able to identify the type of data you have so that you'll know what visual representations are available. We'll cover those other types of visual representations in another video.